Okay, so from now on, our go-to method for writing any electron configuration is going to be to use the periodic table to help us. So just remember that this bit right here is the S block. Okay, so any element in group 1 that is corresponding to an NS1 configuration, okay? So where N is the number of the period, okay, which corresponds to the principal quantum number too, right? So that is our S block right here. Da, 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 da. And then over the right-hand side of the periodic table, this is the P block. So notice there's six um, groups in the P block corresponding to P1, P2, P3, P4, P5, P6 configurations, okay? So this is the P block. Okay, so like for any element in the P block, that will be an NP1, NP2, NP3, NP4, NP5, NP6 configuration, and N will depend on what period you're in. So periods are numbered. One. Hello, that's not a one. Come here. One, two. Get over there. Three, all the way through to seven, right? So just remember your period numbers and you'll always be able to write your electronic configuration. So I don't want you guys trying to do any like memorization of like, oh, we fill this, then that, then blah, 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 blah. This is literally what the periodic table is here for you. There's so much information in it, as well as just molar masses, but it actually gives you all the electronic configurations. So we're going to use NL notation or Chapelle notation, and the superscript tells you how many electrons there are. So write the electronic configuration for a neutral atom of nitrogen. So you find nitrogen in the periodic table. Here it is. And then you're just going to start at the beginning and start reading across. So 1s1, 1s2. It's filled, okay? So we got 1s superscript 2. You know what? I'm just going to write it there. That's supposed to be a superscript, okay? I'll do that for a superscript. 1s2, and then what's next? 2s1, 2s2, but z equals 3 and 4. So 2s2, and then we move across. So you just keep going left to right, and then 2p1, 2, 3 gets us to nitrogen. So 2p superscript 3. So that is your electronic configuration for your neutral atom of nitrogen, okay? It's that simple. We'll start using condensed configurations in a little bit, where you use the inner core configuration of the noble gas at the end of the period above. But for this question, that's not what it's asking for. Just as an FYI, the core configuration of nitrogen, this would take care of that 1s2, and then it'd be 2s2, 2p6, just as an FYI. Okay, so I'm going to do a couple of these because honestly, they don't take very long once you know what you're doing. Okay, so a sodium cation with a charge of +1. Okay, so when you're dealing with an ion, just remember a charge of +1 means it's lost an electron. Okay, so what I should do, ideally, is write the configuration for just the sodium atom first. Okay, so sodium is here, so I can see straight away that that is 3s1. It is going to be my valence electron. Everything before that is my core electrons. Okay, so sodium will be 1s2, and then across period 2, 2s2, 2p6. So that would actually correspond to a core configuration for our core notation. And then we have 3s1, okay? But the sodium cation is going to have lost an electron. You always lose the highest energy electron. That's going to be costing the least to lose. So it will always be that valence electron that's going to be lost. So in that case, it's going to have lost the 3s1 electron. The sodium 1 cation would be this. In terms of core notation, for sodium, that would be neon, would be the core notation, and 3s1. And then for sodium plus, that would then just be the neon configuration. So it's very simple to see when you use condensed configurations how that has achieved noble gas configuration. Okay, let's see if I can find an anion just so we're comfortable with doing anions. Show me an anion, blah, blah, blah. So cation loses an electron, lithium cation loses an electron, da, 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 da. Give me an anion. Okay. All right, if you don't give me one, I'm going to just make one. Carbon anion. Okay, so let's find carbon on the periodic table. Okay, so carbon is right here next to nitrogen. Okay, so well, the best practice is to write the carbon atom first. Use the periodic table, so 1s1, 1s2, 2s1, 2s2, 2p1, 2. Okay, so 1s2, 2s, 2, 2p2 would be carbon. But the carbon anion has gained a negative charge, so it must have gained an electron, and this 2p subshell is not full. Okay, so if p has less than 6, or if a 2 has less than, sorry, or if an s has less than 2, then you've got space to put another electron in for that -1 charge. So whenever you're forming an anion, that electron or electrons it gains will go into the lowest energy orbital that is not filled. So in this case, it'll be the 2p. So 1s2 is full, thank you. Moving on, 2s2, also full. And then we'll have a 2p3 configuration where it is gained an anion, okay? So remember, Alex is wanting to write out full electronic configurations at this stage of the game. But just as an FYI, for a shortcut later on, we'll start dealing with condensed electronic configurations. So carbon would be just helium 2p2, and carbon minus would be helium 2p3, where it's gained an electron. Okay, hopefully that's enough for you guys to get the hang of it.